All right, so told you over the weekend you were supposed to look at the little numbers on whatever plastics recyclables you used. So I brought, in case you didn't do that, I brought you some examples. Anyway, we'll talk about what each of these are, but we're going to talk today about radical polymerization, the use of radicals to generate polymers. And again, one thing you're going to be uncomfortable with is the fact that we're going to focus on the propagation steps, not on the initiation step and not on the termination step. And the reason for that is that the initiation and the termination steps are relatively rare. I'll talk about them briefly, but for our purposes today, we'll focus on the propagation steps and the structure of the polymers. So let's see. Oh, yeah, let's just bring that up. All right, so what is radical polymerization? Well, as we talked about last time, a lot of radical reactions involve repeating steps, and so you could envision a situation in which a radical molecule would add to another molecule and generate a chain reaction like I'll show you here. So this is called radical polymerization. And we'll start with a simple alkene. This is called vinyl chloride because it has the chloride at the vinyl carbon on an olefin. And people call the individual subunit that gets linked together to form a polymer, they call this a monomer, as opposed to a polymer because it's just one. All right, so in radical initiation or in radical polymerization, you need some kind of initiator. And often, I told you what some of those initiators can be last time, but the polymer ends up being so large that the initiating group is only a very, very small portion of the polymer, and so people generally just forget about it. If you're dealing with a chain that's really, really long, most of your molecule is the actual chain and not the ends. And so we don't worry so much about the end groups, and they don't really affect the structure of the polymer that much. So you have an unpaired electron, and then you have this olefin. Now, if you were to predict HOMO attacks LUMO, here you've got a radical, and we've talked about radicals as electron deficient species. If this were a full-on positively charged electrophile, you'd be okay with the pi electrons attacking the electrophile. We've done that a ton of times in chapter 10. So something similar is going to happen here, only it's single electron chemistry. One of the electrons from the pi bond will join with one of the electrons from the radical and generate a new sigma bond. So I'm going to show that bond in red. And then what's left behind, oops, that's kind of fun. What's left behind is the other carbon. Now notice that I chose to put the new bond, the new sigma bond with, I don't know what we should call these, carbon 2 of the olefin. Whoa, suddenly I'm not counting correctly. The reason I chose to do that is to put the radical on the carbon that is also connected to the chloride. Any reason you can see why that might be a good idea? Go ahead.
Create potential for another monomer to attach.
Okay, sure. I mean, we want to make a polymer, and so you can see that if we have a radical here, we can then bring in another monomer and have it react. But I'm talking about regioselectivity. We might have made the bond between R and carbon with 1 instead of 2. There's a reason we chose 2 and not 1. Yeah? Chlorine is more electronegative than the carbon. Now, should that add the radical? Should that allow the radical to be more stable? We talked about radicals last time as being, whoa, that's something else. electron deficient species. Do you remember radical stability tracks with carbocation stability? So from that perspective, putting it next to something electronegative, you might think could be kind of bad. But what do you know about heteroatoms with lone pairs on them? There's something else. It's not electronegativity. It's not, certainly not hyperconjugation. Starts with an R and rhymes with resonance. Right. So if we put the radical on the carbon that's adjacent to the chlorine, we've got resonance stabilization of the radical. See, now it's on the chloro instead of on the carbon. So that controls the regioselectivity of the radical addition to an alkene process. If this were in chapter 10, we would call that Markovnikov selectivity. All right, but you see that that positions us now so that we're ready for a subsequent polymerization step, where another monomer of vinyl chloride can come in, generate a new sigma bond, and again, whoops, why do we keep going? Oh, here we are. Sorry. We'll make a new sigma bond, and again, what we've generated is the Markovnikov selectivity that gives us the more stable radical. In red, I'm including the new bonds that we've made. Here's our new radical. So you can see the pattern that's emerging with each of these, and these are all propagation steps, right? You start with one radical, you end up with another one, you add another monomer, and so on. And so after many, many, many steps, what you've got are these 2 carbon units, each of which is bonded to a chlorine, and then you have the bonds between the 2 carbon units along with your, let's see, we want that to be radical initiator. Sorry, if I'd drawn this better, those bonds would all be the same length. All right, so that goes on and on and on for a long amount of time. The number of subunits in the monomer can be determined by a lot of different things. We'll use just the letter N to represent the fact that you've got tons of these, and N can be in the hundreds to thousands to hundreds of thousands. We'll talk about how you can control chain length, but at some point the process has to end. And there are a couple of different ways it can end. So for termination, you might have 2 different long chain radicals find each other and couple together. And this means this termination step would tend to break the typical pattern between, this would break the pattern of sort of alternating carbons with chlorines on them, because at the end you would bring those 2 radicals together and they both have chlorines on them. Alternatively, I suppose one of the long chain radicals could pull a hydrogen off of something. I'm not sure what that something would be, so I'm just going to put an X there, but you could have sort of hydrogen abstraction. Or alternatively, you could imagine one of the initiators finding the long chain radical to give you something like that. So there's what I'm trying to communicate is there's going to be a lot of diversity in the identity of the end groups on these polymers. But as I said, most of the polymer is going to be this long chain, and so we don't really worry about what the end groups are. In fact, when people draw the structure of polymers like this, they will often just use squiggly lines to indicate where the polymer goes off into infinity. And they won't necessarily worry about what those end groups are. Okay. So the polymer I've drawn for you here is called polyvinyl chloride, or PVC. So this has lots of uses that you might be familiar with. I had a student in a previous class that swore up and down that Taylor Swift sounded way better on vinyl than on electronic stuff. Maybe it doesn't apply just to Ms. Swift. I imagine everybody sounds better on vinyl, but who knows. Let's see. I haven't actually done the experiment, so maybe you want to go home and try that, and you can report to us. Another place you may have seen PVC is at the hardware store, sprinkler parts. So these are the bane of my existence. When we moved into, so this is a fitting on a PVC pipe, and PVC as a polymer is relatively rigid, but it's also somewhat brittle, and this is a problem if you try to use it in situations where the polymer is going to need to expand in the presence of water and so on. So anyway, a lot of fun battles between me and PVC over the years. Let's see, what's the most recent one? No, the funnest one was, so I think it was the first summer that we lived here. It was the first summer and winter that we lived here. Moved here in 2011. And our sprinkler system, I guess, had been designed by somebody who, I think there are things you can do to avoid this, but they hadn't done it. And in any case, you're supposed to, when winter comes, blow out your sprinkler system, which means, any of you that come from the Midwest have no idea what a sprinkler system even is. It's called the rain out there. But here in the West, you need to water stuff in order for it to stay alive. Anyway, so come winter, you need to actually push compressed air through your sprinkler pipes to prevent them from freezing. You don't want water to be in there and freezing because, of course, water expands when it freezes, and PVC is somewhat brittle, meaning that when water expands in it, the PVC actually cracks. So it's always a moment of truth at our house when you go to re-pressurize the sprinkler system after the winter, and you sort of just see what's wrong with the whole thing. Well, one year, got things started and was testing the sprinkler system, turned on the zone in the front yard, and is this in the book of Ezekiel or in the book of Revelation? It may be both. You know where it talks about how like water is gushing out from under the steps of the temple and like healing the Dead Sea, and you go out and it's ankle deep and then it's knee deep? Well, actually the front lawn of our house literally lifted up and water was gushing out from underneath it. And it was not a particularly spiritual experience. In fact, there were a lot of words exchanged between me and the PVC pipes. But what had happened is I had not blown out the sprinklers that year. And so as I dug up the pipe and pulled it out of the ground, it was literally shredded. Like it had cracked in, it was like somebody had taken it and twisted and popped all over the place. Anyway, the lawn still sort of sags in that area as a permanent reminder of my stupidity. So, PVC pipe, kind of fun. Let's see. All right, so let's see what else we've got in terms of polymers that you might encounter in your day-to-day life. Let's see, anything else? Anything I'm missing for PVC? Vinyl records, pipe. What's that? Marshmallow guns. Like that? Okay. Potato cannon, okay, good. Marshmallow guns, they're not good for very long, right? Because the marshmallows get all sticky and then they won't even come. Yeah, okay. That's right. Let's see. So a lot of polymers that are used in plastics have this same basic structure of a 2-carbon subunit, and they differ in the identity of the group that's on one of those carbons. and yet that difference can have quite a dramatic impact in terms of the function of the polymer and its structure. So polymerization is one of those areas where you can learn an important principle for chemistry in general, and it's one that applies to biology as well, and that is structure determines function. This is one of these big ideas actually that applies in a lot of different areas, but the identity, the structure of the polymer is going to determine its properties and function. So let me show you another kind of polymer. If instead we don't use a chloride but just use hydrogens, this is called ethylene or ethene, but nobody calls it ethene, it's just called ethylene. And if you do radical polymerization on ethylene, you end up with something called polyethylene, or PE. And this is just two carbons linked together like this. I don't know why the one bond's longer than the other. It shouldn't be, so my apologies. All right, polyethylene, somewhat boring. It actually comes in a couple of different varieties. One of the things that I didn't tell you about above in talking about polyvinyl chloride is the possibility for radical cross-linking. So do you remember I showed you a potential, oops, we don't want to record that, potential termination step in which the long chain radical abstracted a hydrogen from some other source? Now I'm going to tell you what that some other source is. So imagine that a growing polymer chain radical encounters at some rate, and I don't know what the rate of this encounter is, abstracts a hydrogen atom from, not from just something else, but actually from a long chain, or from one of the hydrogens in the backbone of the polymer. Now you have a radical not at the end of the chain, but in the middle. And at this point, you can actually start growing a new radical chain off the side of this molecule. So let's see, let's copy and paste a bit. So there we have a new bond. Here's a new 2-carbon unit and another radical, and then you can react that with another monomer like I showed you previously. And then you've got a second chain that is going to grow and propagate off the first chain. This is called branching or cross-linking. And if this happens enough, it changes the structure and properties of the polymer. So I'm just going to show you an example of a highly cross-linked polyethylene polymer. We're going to use squiggly lines to represent sort of going off into infinity, and I'm going to highlight individual monomer subunits just so you can see the 2-carbon repeating pattern. And then here's, I guess I should use a different color for that. Here's a second cross-linked chain, and that itself can be linked to another one. And so you can imagine that if this happens enough, you end up with a fairly rigid pattern of, a fairly rigid network of carbon chains. Alternatively, if the cross-linking doesn't happen, if you can suppress the cross-linking, what you end up with are fairly linear chains, not connected to each other covalently, but interacting with each other via non-covalent interactions. And in this case, that would be van der Waals interactions, as you learned in chapter 3. Okay, so this would be an example of a not highly cross-linked polyethylene. This would be an example of highly cross-linked polyethylene. Let's talk about properties and what you think would be the difference in properties between these two different structures of the same polymer. All right? So going back to chapter 3, long hydrocarbon chain, interactions between individual chains are going to be because of these van der Waals interactions or dispersion forces or induced dipole interactions. In which situation do you think those interactions are going to be stronger? Go ahead.
The first, because they're closer.
Okay, in the first you can get closer approach of individual polymer chains. We might say higher contact surface area. Remember, the dispersion forces or the van der Waals interactions are all about the electron clouds in these polymers getting close enough to each other to influence each other such that we have in one case a little bit of negative charge on one side, in the other case a little bit of positive charge on the one side. Those are the van der Waals interactions you learned about. Over here, the crosslink itself is going to prevent close approach of some of those chains. So the not highly cross-linked polyethylene is sometimes referred to as high-density polyethylene, or HDPE. And this shows up on your recycle table as 2. I can't remember what the numbers mean other than it doesn't really have to do with ease of recycling, or maybe it does, I forget. Anyway, you see a 2 on something and that's what it is. So this has a 2 on the bottom. This is, we got tons of these around our house. This is Amber's favorite brand of gum, and all of the boys like steal it from her, so they're always empty. I detest gum, actually. I had braces when I was a teenager and just got out of the habit, and then it seemed disgusting to me. So anyway, somewhat rigid, has different properties from low density polyethylene. Let's see. They've got the little recycle symbol here, but they don't have a number in it. I guess that's what you get when you buy water bottles from Costco. Anyway, this is likely low density polyethylene. Presumably this is what was being talked about in general conference, where we learned the true and living way to crush one's water bottle or something like that. Different properties though, right? Low density, or let's see, the low density polyethylene would be the highly cross-linked version. Because the intermolecular forces are not as strong, it's more malleable and easier to distort in shape. So LDPE, or low density polyethylene. Let's see if I can, I don't know what number that is actually. I don't have it on my list. Oh yes I do, it's 4. So if you see something that's plastic and it has a little number 4 in the recycling triangle, which I can't draw, that's what it is. And the reason that it's more malleable and flexible and easier to distort is because of the cross-linking, which prevents the polymer chains from coming together quite as tightly. All right. I think they should have got a video, shouldn't they, of President Nelson actually crushing that? That would have been much more effective than us just hearing about it. Maybe we can, somebody want to tweet and see whether they'll be responsive to that, I don't know. Okay, questions so far about polymerization? Anything else you want to know about? No? Okay. Oh, sorry, go ahead.
Does this have use in like industrial settings?
Does it have use where?
I'm just thinking of like how like with the epoxide ring opening we have this network.
Yeah.
Like interlinking things. And I'm thinking of like in industrial coatings they use like a lot of epoxides for like factory floors and used for like low density polyethylene in that sense, or is it mostly just like plastics, like saran wrap type stuff?
That's a good question. Low density polyethylene. Let's see if we can figure out some more uses, because I told you what I know. I think you're referring to the fact that epoxide coatings are used a lot in a lot of different areas, and not totally sure. Low density polyethylene was first produced in 1933. So actually the cross-linking thing is easy to do. It just happens naturally. So it's used all over, but mostly for containers and stuff. In terms of whether it might have use for like coating of various high performance surfaces, that's a good question. That's mostly an engineering question, and I guess I don't have a good answer for why. Incidentally, products can be formulated, plastics can be formulated in different ways and processed in different ways. To get them to adopt particular shapes, you simply heat them up, and then you can extrude them through some industrial process, put them in some kind of mold. The grocery bag, actually, if you look on it, is high-density polyethylene. So you might be thinking, what the heck, what's going on there? I thought you said high-density polyethylene was really rigid, and it is in certain formulations, though you can rip it apart like that. Though it's not universally, it's weird, because it's not, plastic bags aren't universally rip-apartable in all directions. Like this direction, which is the useful one, right? You're pulling against this side. It'd be terrible if they ripped easily in that direction. Still got it. Yeah, thanks. Okay. So let's deal with some other polymers that you might encounter. The double bond that has a benzene ring or a phenyl group on it is called styrene. And therefore, the polymer that you get from linking two carbons with a phenyl group on them is called polystyrene. Dang it. There we go. So I'm just going to draw all of the polymers that I'm talking about today could be, because they come from this radical polymerization process, all of them can experience the kind of cross-linking that leads to low-density polyethylene. In terms of whether and how to avoid that, there are specific things you can do, but that'll be beyond the scope of what we want to talk about. So if you see the abbreviation PS on your plastics, that's polystyrene. It's a 6 code in the recycling triangle. It's used for a lot of different things. So here we have the imitation purple Solo cup. This is from Hefty. And it's got a 6 on the bottom of it, which you can't see. So this is polystyrene. Properties are a little bit different from that of PVC or even from polyethylene. You can make the comparison. A lot of plastic cutlery is polystyrene as well. Sometimes these aren't labeled. Polystyrene has a lot of different uses all over the place. Its structure tends to be more brittle than like polyethylene, a little bit more rigid. It's often used in packing materials. If you get, you guys have never done shrinky dinks, have you? Yes? This takes me back to COVID. We were bored, and so all of a sudden, like, Hobby Lobby became a place that we could entertain our children. So yeah, you can buy these little sheets of polystyrene, which you color, make whatever you want, then you cut it out, you stick it in the oven, you heat it up, and it shrinks. And the reason that happens is because the process of smoothing out a plate of polystyrene basically by heating it up, you're allowing the chains to move around and adopt a much more compact state where there's more and tighter intermolecular forces. So I should have brought in, I didn't think to, but I have like the Mandalorian mythosaur insignia that I drew and then shrunk it, and it was kind of cool, and then I didn't know what to do with it, because what are you going to do with something that's shrunk and kind of boring? So let's see, Teflon is also one of these. If you take tetrafluoroethylene and then polymerize it, you now have, again, the same alternating pattern of carbons, only in this case, all of them have fluorines on them. And the carbon-fluorine bond is interesting. It's a very strong bond. Fluorine's very electronegative. It's not that happy to share its electrons. And so fluorine really doesn't engage as well in intermolecular interactions as a lot of other elements do. And what that means is stuff doesn't stick to fluorine modified surfaces as tightly as it can to other things. Fluorine's really bizarre. If you put water on a surface that's been coated with Teflon, the water beads up and doesn't interact with the surface at all because it can't hydrogen bond very well with the surface. But at the same time, you put grease on fluorine, on a fluorinated surface, and it also doesn't really spread and interact well with the surface. And so Teflon's used in situations where surfaces are going to encounter both grease and water to keep debris from sticking. I don't know, it's an open question to how well it works. A lot of pots and pans are coated with Teflon nowadays. That doesn't seem to prevent you from having to scrape the surface anyway, but yeah.
Isn't it also kind of carcinogenic?
Is Teflon carcinogenic? Well, let's look that up. I don't know. I'm still here. But they got a lot of years before that kind of thing would kick in. So, is Teflon carcinogenic? Do you ever wonder what you're paying for when your professor Googles stuff in front of you? Technically, there are no health concerns with Teflon. Huh. Who knows? All right. So speaking of things that you eat occasionally, let's talk about Elmer's glue. None of you does that anymore, presumably. Elmer's glue is this same kind of vinyl polymer, but the polymer is called vinyl acetate. And when polymerized, it's called polyvinyl acetate. And this is an interesting polymer because you can use it for some different purposes. Running out of space for all of these acetate groups on alternating carbons. Yikes. All right, so radical polymerization, it tends to solidify in air, so presumably air provides the radicals. PVA is what it's called. You tend to find this in Elmer's glue and wood glue. Interestingly though, these ester linkages can be hydrolyzed, and so you can convert polyvinyl acetate into polyvinyl alcohol, which has some other properties as well. And so there's a number of different uses. None of you know what an envelope even is, but back in the day when you wanted to send a letter, you had to lick the adhesive, or if you were fastidious about that kind of thing, you could get a little sponge and wet the adhesive and then seal it. But it's apparently considered safe because nobody's worried about licking envelope adhesive or eating Elmer's glue. All right. Paint. Some kinds of paint involve something that's called acrylate. And so acrylates in general are molecules with this kind of structure. And whatever this OR group is, it could be any number of different things.
But when polymerized, it follows this same pattern of alternating carbons. And so if you hear of people talking about working with acrylic paints, like this that you can get at Hobby Lobby, acrylic paint, that's polymerization. As it dries, you get polymerization to get a structure that's kind of like this. Okay. Yeah. Say it louder, sorry.
This might have already been answered before, but how long are the polymer chains?
Okay, how long are the polymer chains usually? Let's talk about how you could control that. In some ways, it's a stoichiometry problem. Okay, suppose you have, just for the sake of discussion, suppose you have 100 molecules of vinyl chloride per 1 molecule of initiator. How long's your chain going to be? 100, right? If the termination events are slow, that means that as long as there's a radical present, the chain is going to lengthen. And so your chain can go as long as you have monomers for each initiator. So supposing I only had 100 molecules of vinyl chloride, but I didn't want the chain to be 100 long, I wanted it to be 50 long, I would just need to up the amount of initiator to 2. And then I would get shorter chains, or maybe 4, and then I would get even shorter chains. So you can control the length of the polymer by the ratio of initiator to monomer. You could also include what are called radical traps. These are molecules that react pretty rapidly with radicals, and that could intercept the growing radical chain and stop it, and that would tend to make you move towards shorter chains. Okay, what else? Yeah?
Does it ever go off the chlorine that has the radical electron from the resonance?
Do we ever branch off, you got resonance stabilized radical here like I showed you, would it ever branch off from there? No, because that would ultimately result in a chlorine that was bonded to 2 things, which isn't really a stable situation. Yep, go ahead. Okay. A specific follow-up question, or just want me to say it again? Okay. If we assume that for the most part, this radical is stable enough to last for a while, then the thing that determines the length of the polymer is really how much monomer we have for every radical present in the reaction mixture. So supposing we had 100 monomers and 1 radical initiator, we could get a 100 long chain. And then if we wanted to go shorter than that, we could double up or triple up on the radical initiator. If we wanted to go longer than that, we could add more monomer. And so yeah, you can to some extent control the length of the polymer based on how much initiator you put in versus monomer. I will say that all of this is not as controlled as you might like, and so when you make a polymer, you end up with a population of polymers that vary in length. So if we put here N for number of monomers, and here we have on the y-axis something like population. Supposing we decided, okay, on average I want 10,000 monomers for every 1 initiator. The average length of the polymer is probably going to be around 10,000, but there's going to be some kind of distribution of polymer lengths. And that's called polydispersity. It means that it's very, very difficult to get like a polymer that's exact where all of the polymers in a sample are exactly, say, 10,000 units long. You have some range of acceptable values. Yeah?
I have 2 questions. So So one, how does the length of the polymer affect the properties? And then
Okay.
the other one is like, is there a way to then like, if you've got this like range of polymer lengths, is there a way to then like sort those out so that like in manufacturing you can end up with more of whatever desired length you want?
Yeah, is there a way to control length, and how does length affect properties? It's a good question. I don't have a good example for how length affects properties, other than to say that that you would predict the same sort of thing that we talked about with hydrocarbon length to apply. That is, the longer a molecule is, the stronger the intermolecular forces can be. In terms of how do you separate out the polymers, I think that's actually quite difficult to do, especially if the polymers are soluble in some kind of solvent or are themselves liquids. There are things you can do. In the solid state, separating out polymers of different sizes is difficult to do practically. And so what I think people do is they try to control the polymerization process to get this peak to be as narrow as possible so you don't have to worry about it. Okay, good. Others? Okay. We got any aspiring dentists out there? Some? Yeah? Okay. So if you intend to spend time in the future with your hands tinkering with somebody else's teeth, then you're going to be doing a radical polymerization reaction all the time. So if you've ever been in the dentist's chair and getting a filling, after they do all the nasty drilling and packing in the stuff, there's usually a phase at which somebody takes what looks like a gun that has a little blue light at the end of it and a yellow shield, I think, to protect the eyes of the person using the instrument. They stick it in your mouth, they push the button, and then they pull it out of your mouth, and then they're done. And what's actually going on in that is they're using UV light at the end of this LED weapon to polymerize some of the filling. I don't know. I've never actually done it. I mean, I've watched it happen to me, but I've never been the one wielding the LED gun of doom, so I can't say how actually fun it is. What I'm going to draw for you now is called BPA glycidyl methacrylate, or bis-GMA, and this is a component in dental filling composite. All right, so that's the acrylate portion. Here's the glycidyl portion, a 3-carbon chain. And then here is the BPA portion. We've talked about bisphenol A before, but this is actually a component of dental composite. So this one is cool because you've got 2 different vinyl type groups that are prone to radical polymerization in the same molecule. So this is designed to generate cross-linking. All right, so that's bis-GMA or BPA glycidyl methacrylate. You don't care, and neither do I at this point what it's called. For our purposes, I'm going to circle all of this, and we're going to because of the blue light that's used, let's color the whole thing blue, and and then we'll abbreviate it, okay? Notice those end groups though. Notice that on either end you've got a 2-carbon bit that's like a vinyl polymer, right? And so in the presence of UV light, you can generate, you can initiate radical polymerization, and you're going to have the 2-carbon zigzag that we showed before for those, what's going on here? For the Teflon and for the
low and high density polyethylene. So you have this kind of zigzagging going on, and then every other carbon, you've got a methyl group, and then you have oops. And then you have the big blue thing that connects one side to the other. And then, shoot, we've totally run out of space here, right? But, what am I going to do about this? Do you care? Can you envision what's going on? Well, all right, whatever. Let's try that. All right, so you've got this ladder of polymers. Here are the individual vinyl units. And you've got them linked together, not only on this side, but then on this side too, to another long chain and so on. And that's what holds your dental filling together. That was not as well illustrated as I might have hoped for, but you got the idea-ish? Yeah. Okay, so that's what's going on inside your teeth when they bring out the blue LED gun of death. You'll notice a particular smell when that happens, and that's actually the acrylate. Has a characteristic smell. Let's see. So those are a bunch of polymers. I want to tell you a little bit about antioxidants because people will be attempting in your life to sell you products based on the presence of antioxidants, so you probably ought to know what those are. But that's all we have time for today, so I will see you Wednesday for our last class.